Hello students, this is Professor Chalai, and in this video we're going to look at hybrid atomic orbitals. As always, you can follow along with our Chapter 8 workbook. And by the end of this video, you should be able to explain atomic orbital hybridization and relate hybrid orbitals to molecular geometry. Let's get started. And so this word, hybridization, when I say we'll explain atomic orbital hybridization, what does that mean? Well, let's look at the definition. Hybridization is simply a process where we have a teaming up, if you will. So it's a teaming up of atomic orbitals when they try to form chemical bonds. And the process by which they do that is called a linear combination of atomic orbitals, or LCAO. And we'll come back to this idea of linear combination of atomic orbitals later on, but simply put, it's just a way of adding up atomic orbitals to create different kinds of orbitals. That's all it is. And let's look at an example or a few examples. Let's look at beryllium chloride in BeCl2. So in beryllium chloride, we have beryllium, which has electron configuration 2s2, helium and 2s2, and its 2p orbitals are completely empty, right? That's beryllium. And in our previous video, we talked about how valence bond theory talks about bonds forming when there is overlap of atomic orbitals that are not paired. But in beryllium, there is no unpaired electron. So how can beryllium then form this bond? It has no unpaired electrons to help form a bond. Well, what it does is there's a teaming up of orbitals. It moves this electron over here somewhere. And so now you have these two orbitals, let's highlight them, that are teaming up to form two unpaired electrons, two orbitals with unpaired electrons to help form bonds. So now the electron configuration is, instead of this 2s and one of these 2p orbitals, you have two orbitals here, which we'll call, well, it's teaming up one s orbital with one p orbital, so we'll call it an sp hybrid orbital. And then you'll have your two 2p orbitals over there that are left over that are not involved in bonding at all. So that's how it helps to form a bond. You have these two hybrid orbitals, one s and one p, joined together, and now they become sort of inseparable. They have the same energy, and they're just there available for bonding. And so now, if you think about chlorine, right, we know that chlorine has hydrogen, neon, right, with a 3s with two electrons, and a 3p with one unpaired electron there that can then, so if I draw that in green, that can then team up with that sp hybrid orbital. And so this is how beryllium could form a bond with one of the chlorines, and then the second chlorine, the same thing with the other one, and so that's how it forms the bond with the second chlorine atom. And then never forget your lone pair electrons in your Lewis structures. So that's the case of beryllium. It teams up one s orbital and one p orbital to form an sp orbital that's available for bonding. Let's look at another case. Well, before we look at another case, let's just look at that. So sp hybridization means that you have two electron groups available for bonding, right? These two electron groups, they could be bonding or lone paired, but they're teaming up to form two orbitals. And so whenever you have that situation, from Vesper theory, two electron groups means we have a linear geometry. So let's look at a case where we'll have three electron groups by teaming up one s orbital and two p orbitals, for example, in BH3. So boron has electronic structure 2s, 2p, like this, right? So it doesn't have 3 unpaired electron for bonding, so you might be wondering, how is it forming 3 bonds? Well, again, it teams up the s orbital with one of the p orbitals, well, with 2 of the p orbitals to help with bonding. So we have a situation where 3 bonds, 1s and 2p orbitals team up, and then we have another 2p orbital there that is doing nothing, and so these guys are now ready for bonding. And that's why we can form triple bonds with boron in this example. Right, so just note here, we no longer have a 2s and a 2p orbital, we have sp2 orbital, and then this 2p orbital here remains unhybridized. So we'll have 3 electron groups, right, either bonding or not, and so the geometry there will be a trigonal planar geometry. If you want to see pictures of what these orbitals might look like, your textbook has really beautiful pictures of them. Carbon in CH4 teams up one s orbital with 3 p orbitals to form an sp3 hybridization. There are 4 electron groups there, so its structure should be tetrahedral that we learned from Vesper theory. And then you can even have, with 5 electron groups, you have an s orbital, 3 p orbitals, and a d orbital teaming up or hybridizing. And similarly, for 6 electron groups, you have s orbital, 3 p orbitals, and 2 d orbitals teaming up. All right, so with that understanding of how electron groups and hybridizations are related to each other and how those are related to geometries, let's do these problems. For each of them, draw the Lewis structure and then try to figure out what the hybridization is for the atoms that they ask. So I'll start with SO4 2-, the sulfate ion. If you haven't done these, please pause the video and do them first, since we already know how to draw electron group, Lewis structures, and identify electron groups. Okay, so for SO4 2-, we know that we'll put the oxygen on the terminal positions because oxygens are very electronegative. How many valence electrons do we have? Well, sulfur has 6. Let me just verify. Yep, sulfur has 6, oxygen has 6. So that's 6 times 5, right? 1 for sulfur, 4 for the oxygen. Plus there's a 2 negative charge, so we need to add those 2. 6 5s is 30, plus 2 is 32. We have 1, 2, 3, 4 bonds, so that's 8 electrons. If I minus 8 here, I get 24, I believe. So let's add 24 more electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. All right, so we have 24 electrons. Make sure, let's put this in square brackets and put a 2- there so that we don't forget our charge. All right, so you might be thinking this is fine. This is happy. All the things, all of the atoms have filled octet, but you might, if you do the formal charge, you'll recognize that each of these oxygens have a -1 charge, and the sulfur has a +2 charge. We know that sulfur could fit more than 8 electrons, so what will end up happening is some of these oxygen, and I didn't want to erase the whole oxygen, will share some of their electrons. Let me draw back the square bracket. And whichever one shares, it actually sets up hybrid structures that we talked about a few lectures ago, which again has nothing to do with hybridization that we're talking about in this section. Hybrid structures, or resonance structures rather, would be set up with different oxygen forming double bonds with sulfur at different times. So in this situation, the sulfur has a 0 formal charge, these 2 oxygens have 0 formal charge, these 2 oxygens will have a negative charge, and that will change with the different resonance structures you could draw. Okay, so this is our structure for sulfur in SO4 2-. How many electron groups is around sulfur? Remember, every bond, whether it's single, double, or triple, comes as 1 electron group. And so we have 1, 2, 3, 4 electron groups. This means that we have an sp3 hybridization. All right, let's do some more examples. If you haven't done these yet, please, again, pause the video and try to figure it out first on your own. All right, so we got nitrogen with 2 hydrogens coming to it. That nitrogen is connected to oxygen. This little parentheses here, if you haven't figured it out, means that the oxygen is connected to the carbon, and then this nitrogen is also connected to the carbon. So I'll draw it sort of like this. This is the skeletal structure if you weren't able to figure it out at first. Now you can pause the video again and try to finish up the Lewis structure. All right, so let's see. Hydrogen has 1 valence electron, and how many hydrogens do we have? 4, okay. Carbon here has 4 valence electrons. Nitrogen has 5, and there's 2 of them. And oxygen has 6. So what's the valence electrons we're working with? 4 here, plus 4 is 8, plus 5 is plus 10 is 18, plus 6 is 24. How many bonds do we already have? 1, 2, 3, 4, 5, 6, 7 bonds. 7, 2 is 14. So we're left with 10 electrons to distribute. And you know I'm going to put them on oxygen first. So 2, 4, 6. Then I'm going to put them on nitrogen second. 8, 10. All right. So what do we have? What do we have? Well, the carbon in the center doesn't have a valence electron. It needs a fill octet. So what are all the possibilities? This nitrogen could share 2, this nitrogen could share 2, or this oxygen could share 2. Well, which one do we think would happen? If currently this nitrogen, the formal charge is 5, right? 5 valence electrons for nitrogen minus 2 dots and 3, 6 is 0. Currently, this nitrogen is also 0. And currently, this oxygen, if it doesn't share, is minus 1. The carbon is plus 1, right? If the nitrogens share electrons, it's going to have a formal charge, right? It's going to lose an electron because the 2 valence non-bonding electrons would form a single bond, and so the formal charge of nitrogen will become plus 1. So we probably don't want that. In fact, what's more helpful is if oxygen shares its electron to form a double bond here, and now nobody has a formal charge. And this is the situation we end up with. Okay, now the question is asking us for what is the hybridization of the carbon in this structure? Well, let's count the number of electron groups around the carbon. Every bond is 1, so 1, 2, 3, has no lone pairs. So 3 electron groups, you can bet it's sp2 hybridization, and the structure will be trigonal planar. All right, let's try some more. SO3. If you haven't done it so, please do this first. But SO3, valence electrons, 6 from the sulfur, 6 from the oxygen. So 6, 4 is 24. We got 1, 2, 3 bonds. That's 6 electrons. That's 18 remaining for distribution. I think my math is correct. So let's put the 18 starting with oxygen. So 2, 4, 6, 8, 10, 12, 14, 16, 18. All right. So as you can probably guess, each of these oxygen now has a -1 formal charge, and the formal charge on sulfur is +3. So we know that sulfur could fit more than just 6, well, it has 6 electrons, valence electrons now, but it could fit more than 8 even. So what if we share those 2? Didn't mean to erase the oxygen. What if we also share 2 from over here? That will make the formal charge on this oxygen 0, and then we can share 2 from over here, making that formal charge of that oxygen 0 as well. Now the formal charge of sulfur is 1, 2, 3, 4, 5, 6, 0, right? 6 minus 6 sticks. And the formal charge of each of the oxygen is also 0. So this is the structure of SO3. But we're interested in hybridization. How many electron groups? 1, 2, 3. So the hybridization here is going to be sp2 again, right? Trigonal planar structure. All right, let's finally look at carbon and carbon dioxide. We've done this one before, right? We know that it'll set up a double bond, and then oxygen will have 2 lone pairs each, but we're interested in hybridization. Just 2 electron groups around the carbon, So the hybridization here would be sp hybridization. It's a linear molecule. We talked about that before. Carbon dioxide is just a molecule that's in a straight line. All right, so that will bring us to the end of hybridization. So to figure out what hybridization it is, just count the number of electron groups. Remember, electron groups are bonds or lone pairs. Every bond count as one. Doesn't matter if it's a single, double, or triple. They're all just one electron group. And every lone pair, if there exists lone pair, is also counted as a single electron group. From that, we can figure out the hybridization and also the geometry of the molecule. All right, so that will bring us to the end of this video. In our next video, we're going to look at multiple bonds and this idea of electron delocalization. I'll see you then. Bye.